If we could move quickly to take seats, please. We're under a bit of a schedule. Well, hello everyone. My name is Michael Bostock, and on behalf of my co-chair, Joan Gomberg, I welcome you to SSA 2019 here in Seattle. It is my distinct pleasure this afternoon to introduce today's opening keynote speaker, Dr. Bruce Banerdt, who many of you will recognize as the principal investigator for the Mars InSight mission and a planetary geophysicist at NASA's Jet Propulsion Laboratory. Bruce graduated with BSc and PhD degrees from the University of Southern California, from whence he took his position at NASA in 1977. His research focuses on the geological evolution of Mars and other terrestrial planets, and he undertakes his research with a variety of tools from the geophysical arsenal that include potential fields, gravity and magnetics, satellite altimetry, and of course seismology. Bruce has been involved in a number of missions, and in particular in the instrumentation of those missions. I will highlight the Mars Orbital Laser Altimeter, or MOLA altimeters, on the Mars and Observer and Mars Global Surveyor missions, the Synthetic Aperture Radar on Venus Magellan, and the seismometer on the CNES Netlander mission. And he also served as project scientist for the Spirit and Opportunity rovers for 6 years. You're probably like me, you are waiting with bated breath for some of the first pictures of seismograms from Mars, and so without further ado, I give you Bruce Banerdt.
Thank you, Michael. So I am really thrilled to be here this afternoon. I've been spending about 30 years talking about what we're going to do on Mars, and finally get to talk about what we're doing. So let's go ahead here. So we think of InSight as a space mission, but it's really more of a time machine, right? So we're going back more than 100 years back to the turn of the 19th to the 20th century to answer the basic questions about a new planet. You know, what's the thickness of the crust? What's the structure of the mantle? The size and density of the core, and the distribution of seismicity. These are questions that were sort of laid to rest a long time ago on the Earth. But it also lets us go back even farther, like 4.5 billion years back to the birth of the solar system, and we can use this information that we get about Mars, the structure of Mars, to inform our understanding of how the planet's formed, the processes in the first few tens of millions of years of planetary formation that transformed these planets from balls of kind of chondritic material into the very intricately structured objects we have today. Understanding that process, we think, is particularly well done at Mars, because we think that Mars actually retains the fingerprints of those processes much better than the Earth does with plate tectonics and mantle convection kind of stirring everything up. We actually think that a lot of these primary structures really are still there on Mars. So we go back, so through history, so the first remote detection of an earthquake back in 1889, that was, let's see, 130 years ago, 140 years ago, almost exactly. We are now looking at our first remote detection of a Mars quake. Detection of the Earth's core just about 17 years later, followed by the thickness of the crust. It took about 15, 20 years to do these things. We were hoping to squeeze that all up a little bit. And finally, detection of the Earth's inner core. That might be a little bit of a stretch for InSight, but we can hope. And of course, the distribution of the Earth's seismicity. So all sort of the basic building blocks of the seismic structure of the Earth were in place before 1950. And we went through sort of a similar kind of a process with the Moon. And here we are doing the same thing for Mars. So here's what's sort of a comparison of the Earth, Moon, and Mars structure. I think the most important thing of this diagram are these question marks. So we've got a nice sharp picture here, but actually all these boundaries are fuzzy within factors of 2 in some cases. So we don't know what the core is to plus or minus 300 kilometers, the thickness of the crust to within plus or minus a factor of 2. These are all things that we hope to nail down with InSight. And in fact, the goal of InSight is to provide constraints on the formation of the terrestrial planets. So actually, a selling point for this mission was that we weren't just going to Mars. We had to kind of get people to buy in, people from across the planetary exploration program, to buy into supporting this mission. And the buy-in is that we're not just doing a geography mission, making maps of boundaries and so forth. We're actually going to use this to understand some fundamental things about solar system science and solar system history. These are what we call our level 1 requirements. This is what I promised NASA I would do in my proposal. There's like roughly 8 numbers and a couple of other things there. So this comes out to about $100 million per number. Okay, so that's the going rate at numbers at NASA apparently. Okay, so I don't need to go into this very much with this room, but for seismology, of course, we hope to get signals from fault motions, but given that we've never gone to Mars with a very sensitive seismometer, there's no guarantee, of course, that we'll get, there was no guarantee that we would get seismic signals from quakes, but we have other sources that we can depend on. We have impacts. We know that we're going to be impacting Mars on a regular basis, and if you do the calculations of size versus distance and make some assumptions about the seismic efficiency, you can come up with maybe a half a dozen impacts per year that you can use for probing the interior, maybe not very deep into the interior, but certainly into the crust and maybe the upper mantle. We can also measure the Phobos tide. Phobos gives a solid tide to Mars of about 1.5 centimeters or so, and by measuring that really precisely, you can actually look at the size of a liquid core, looking at the variations in the, basically a love number. It's not quite a love number, but it's the gravitational parameter. We can't really measure these frequencies at these frequencies, which is about 7 hours, with our seismometer directly. But given that Phobos goes overhead every 7 hours for 2 years, by stacking that data and doing some careful calibration, we think that we should be able to get some information of the core from the Phobos tide. And of course, the atmospheric excitation is going to set up various different kinds of resonances that we may or may not be able to use. And there's lots of techniques. These are single station techniques are kind of out of vogue on the Earth when you've got 1,000 stations to work with. It's why use one? But there are lots of ways that you can use a single station to actually get a planetary structure, all the way from the very the longest frequencies at the normal modes down to pretty much conventional travel time analysis. With one station, you have to get a little bit clever and use multiple orbits of Rayleigh waves and things like that. But on a small planet, that shouldn't be so much of an issue. We think that we can probably do that with down to magnitude, maybe even magnitude 4 or so. So this is the payload on the InSight lander. We have 3 investigations basically. We have the seismometer, which is kind of the core instrument of the mission. We also have a heat flow probe, which is supposed to penetrate down about 5 meters below the surface with temperature sensors all along the cable, connecting it up to the surface to get the thermal gradient. And by putting calibrated heat pulses into the soil, we can measure the thermal conductivity and get a measure of the heat flux coming out of the planet at a place. And finally, we have a radio science experiment which uses these medium gain antennas on either side of the spacecraft to do precision tracking of the lander as it sits on the surface. And of course, if you're tracking the lander, you're actually tracking the surface of Mars. We track it for about a half an hour a day, more or less every day for a year. And over that half an hour, it describes a little bit of an arc as the planet rotates, and we can get the rotation axis direction. We can track that to a precision of about 10 or 12 centimeters in absolute space at 200 million kilometers away, which is a good trick. but the Deep Space Network is able to do that, and we can do that to get the precession rate and the nutation, or equivalent of the Chandler wobble of Mars. But I'm not going to talk about those two instruments, and I'm not going to talk very much about these other sensors, but we have a complete suite of weather sensors as well, because as you well know, seismometers measure just about everything around better than it measures ground vibrations. So you need to be able to tell, when the wind's blowing, when you have pressure variations, when you have magnetic field variations. All these things are necessary to make sure that you're not misinterpreting noise in your seismic data. Okay, so this is sort of a breakdown of the SEIS instrument. It's a pretty complex instrument, actually. The heart of the instrument is our VVB, our very broadband sensors, and we complement those with a set of short period sensors. So the SPs are good down to 10 seconds and maybe a little bit below, and then up to about 100 hertz. The VVBs are good up to maybe 10 or 20 hertz, and then down to 100 seconds or so. And so between the two of them, we can measure a reasonably wide band of frequencies. They're inside, the VVBs are inside an evacuated sphere, and if you were following the news about 2.5 years ago, you'll know that a leak in this sphere was responsible for delaying our mission by 2 years in order to get that fixed. We went back, we redid that enclosure, and now that's vacuum tight so far. We have a leveling system to do the leveling remotely on Mars, and then the whole thing is together in this sensor head, which gets deployed to the surface. And we have a lot of other sort of subsystems that back us up. Instead of having a nice basement somewhere that we can set this thing up in, we actually have to make our own protection for the seismometer in order to be able to make measurements on the surface. When you have variations in the daily temperature that are up to 80 degrees C during a diurnal cycle, it's a challenge to actually make sub-nanometer measurements in the dirt on another planet. And I like to tell people that any fifth grader can measure 100 picometers in the laboratory. I mean that's simple, but trying to do it in the dirt, in the temperature, in the wind, on another planet, that's harder than it sounds. Okay, so here's our 3 VVBs poised to make our measurements on the surface of Mars. And in order to be able to make these measurements, of course, like I said, we have to isolate it from the elements, from temperature, from wind, and to the extent possible from pressure. So we have 3 layers of protection on it. We have the first layer, which is this inner evacuated sphere. That's a hard vacuum. So the leak that we had in this system last time, if it was on your car tire, it would take about 50 years before you noticed a 1 psi change in the pressure, but that was enough to completely destroy our sensitivity, so we had to fix that. So there's the evacuated sphere. That's our first level of thermal protection. Then we have what we call the RWEB, or remote warm electronics box. That's this kind of thermos bottle that's around it. It's actually kind of a flexible thermos bottle made out of mylar. And then finally, we have our wind and thermal shield, which protects it from the wind. And we have this cool kind of skirt around it with chainmail at the bottom, which actually seals around the bottom, keeps the wind from coming underneath. And this has turned out to be an extremely effective enclosure for our seismometer. Okay, so here's a picture of the instrument deck on Mars. It's a selfie we took on Sol 8 or 12 or something like that. You can see the seismometer sitting here, the wind and thermal shield sitting here. At this point, we've come, like I said, about 200 million kilometers, and yet we're about 1 meter short of where we want to be. Okay, and those of you old enough to remember Viking might have seen this picture. This is the seismometer on Viking 1. We've actually sent seismometers to Mars before, but you don't hear too much about Martian seismology, and that's because the Viking seismometer, okay, so here's the Viking seismometer, this is the Viking deck, there's the ground. I asked my astronomy club presentation, I said, what's wrong with this picture? Okay, you're trying to measure, very fine vibrations of the ground, and you're sitting on the deck of a lander with dampers in all the legs. And so Viking did not work very well as a seismometer, unfortunately, but we decided to fix that problem and deploy it to the surface. And so I've got a sequence of videos to show how that works. So it took us about 3 weeks to map out what we call our workspace, the area that the robotic arm can reach. We have a robot arm that picks this thing up and puts it down. Once we found the place that we wanted to put it, we started the seismometer deployment on Sol 22. Okay, so the first thing we did was just actually put the seismometer on the ground and then let go of it. Pretty standard. Okay, and it'd be great if that was the end of it, but there's still a lot more to do. So the first thing we did after that was to level it, and you have to watch really closely. You'll watch it dip a little bit to the right, boop, there it goes. Turns out that where we landed, it only has a tilt of about 2 degrees, so we didn't have to level it very much, and it's maintained a very stable level since then. After that, we released the tether. You can see the tether or cable is kind of hanging up in the air at this point, so we had to release that, pop down onto the ground, and then we're ready to go on. Turns out noise from the tether was one of the things we were most worried about. It's a very stiff tether. It's a ribbon cable, but it's actually 6 plies, and those plies are each about as thick as your belt. They're not the little, flimsy ones that you see in your computer. And so that is actually a very effective conduit of strain up and down that system. So we worked very hard to figure out ways to isolate that. The first thing we did was we have a tether isolation device we call the load shunt assembly, or LSA. And you can see here, we released it and just kind of twist a little bit. That's really not enough, but if, I don't even know if you can see it over here, but bink, it goes a little bit. And then we pull the seismometer down. So we leveled it in high position, kind of at the top of its legs, in case we had to clear any rocks. There weren't any rocks under it, so we level low and it sits down right there, as far down as we can, so we don't have as much of a resonance in our legs. The next thing we did was do our tether adjustment to actually open up that load shunt. And you can see before and after there, it actually took us a bunch of tries. So we have our robotic arm comes down, figures out exactly where it is, comes back, and then tries to adjust, but we kind of miss because sometimes you miss. Then we did it again, got most of the way, did it a third time, and finally had it open enough so that we now have a loop here that's going to absorb a lot of the strain from thermal variations on that. And finally, once we've done all that, we can put our windshield on it. Now we're up to Sol 70 or so. We started on Sol 20, so it took us almost 2 months to go through this whole installation process, a little bit longer than maybe you would take in a field installation on the Earth. But when you're doing it from 200 million kilometers away, you have to be a little bit careful. All right, so this is sort of a map of the noise evolution of the seismometer. So what we have across here is time from midnight through the day and then to the next midnight, and these are spectrograms. So we have a 5 hertz band here. Red, of course, is noisy. Blue is quiet, and so we started off, we did some operating on the deck, and you can see that it's pretty noisy up here. Once we put it on the ground, immediately the noise went down by an order of magnitude or more. And you can see that we have already a pattern showing up of noisy periods kind of here in the morning and early afternoon, and it's getting fairly quiet at night. And you can see this is acceleration in meters per second squared per root hertz. So we're down close to a nanometer per second squared per root hertz down in here. You can see we released our load shunt here, got a little bit quieter. Finally, we deployed our WTS, and the noise goes way down. This is our short period seismometer, which has a noise floor of about 8.5 times, or about a couple times 10 to the minus 9. Our VVB is about 10 times more sensitive. And in fact, here is some statistics we did on the noise a day or two after we put the wind and thermal shield on there. This is about, I think, an hour of data. And you can see here's the noise that we're getting down to during the quiet part of the night. This is 10 to the minus 10 meters per second squared per root hertz here. This is the Earth low noise model. We're about factor of 10 to the 3 below the low Earth low noise model at a few seconds period. And so this is an extremely quiet environment during the night. Here is a typical day of SP data. Again, this is spectrogram. We're going from 0 to 50 hertz here. You can see resonances here from the spacecraft, resonances with the seismometer with the ground, and you can see lots of kind of mush in here, which is due to weather, basically. A lot of glitches. So we've got lots of stuff to look at. We have over 100 days of this kind of data to look at. So this is a typical day. The time series looks like this, and of course, when you look at this, it's dominated by the wind and by these glitches. You have to really look down into the details of the data to see anything interesting. And speaking of something interesting, this is an atypical day on Mars, and this was the first Mars quake that we identified. So here we are. This is the opening round of Mars seismology. Here is the spectrogram from 0 to 10 hertz. Unfortunately, we don't have the higher frequency data. This is getting clipped off by our anti-aliasing filter at 20 samples per second. But you can see we're coming along. These are our normal resonances we see all the time. But this is our event right here. This is not like anything else we've ever seen in our 140 sols so far of data. It's very reminiscent of a lunar quake, so we are very confident that this is a Mars quake that we've identified. If you've read the press release we put out this morning, we also have 3 other signals that we think are possible quakes. Those of you who are active experimental seismologists, you can probably pull those out right now, right? See 1, 2, 3. I know I can't, but here they are. So these are actually down below a nanometer of displacement. So you would never ever see this anywhere on the Earth, even in an isolated laboratory. It's actually a pretty good trick to test a Mars seismometer on the Earth, if you think about it. With Earth with 9.8 meters per second squared, and you go to Mars at 3.7 or something like that. It was really difficult to figure out a way to test these things. And honestly, I was a little bit relieved when we got to Mars and everything worked right, because you can never actually test it fully on the Earth. But here we are operating at below actually our design spec, and the signals themselves look like this. The real interesting thing, of course, is in the spectra, and you can see that the difference between the noise, which is in black, which is from adjoining windows to this event, and the signal, which is in red, you can see these peaks down here at around 2 to 4 seconds here for this 105 event. This one is a little bit lower, quite a bit lower. This one is actually probably the least certain of being a seismic event, but because it has signal at much lower frequencies than we can really explain. And then the Sol 133, again, we have this stuff up here. And you can compare that with our Sol 128 event, which is the one we're identifying as a Mars quake, with a lot more signal up here at the higher frequencies. So now that we have what we think is a Mars quake, we can start talking about statistics. So we have one sample. We're well into statistics now, right? So, which actually, I've actually given 3 talks right now talking about the statistics of 0 samples. So one sample is more than enough. Okay, so after 140 sols on Mars, we actually only have about 79 sols of good data, because we were on the deck before we put our windshield on. We were really several orders of magnitude above what we'd like to be. So during that time, we have 1 certain Mars quake and 3 candidate effects. And so events. So if we assume that these are small quakes, and I think you can put error bars of at least plus or minus 1.5 on that, depending on the distance, because we have no idea how far away these are. You have some idea. Maybe you can look at the frequency content, but then we don't know what the Q is, and et cetera, et cetera. All this will become clear, I'm sure, in time as we collect more of these. But so if you just assign 2.5 to these, you can have either 4 Mars quakes or 1 Mars quake, and that puts you either on this blue curve here or the red curve, where this is magnitude or number of events as a function of magnitude. And you can get, using Poisson statistics, you can exclude everything in the dark area up here as being at the 90% confidence level as being more a higher rate than we actually are observing, and you can exclude everything down here as being a lower rate at a 90% confidence level. If we have this rate here, we can probably expect another handful of events, maybe a half a dozen over the two-year mission. If we're at this higher rate, maybe a couple of dozen. And so we're sort of in the range where we can have a good shot at being able to address our large-scale questions within the nominal 2 years of this mission. Now, there's nothing on the spacecraft that precludes us from going longer than 2 years. It runs on money, just like everything else in the world. And so we are planning at the end of 2 years to go to NASA and ask them for more money to keep this mission going. We hope to have enough Mars quakes in our pocket by then and enough results in our pocket by then to show them that this is a good cost trade to do. Okay, so what's next? Hello? Oh, data. There are probably people in this room that are interested in seeing this data, and you will see it. NASA has a policy of releasing all the data from its missions on a fairly quick cadence. We have a little bit of grace period here to actually get our pipeline set up, get our calibration in place and so forth. Our first release of data will be at the end of May, end of next month, and that will cover roughly the first 3 months of the mission up through around the end of February. That's going to be uncalibrated data because we don't have all of our calibrations in place yet. The second release in June, a month later, should have the calibrations of that first 3 months of data plus the additional month, and then after that we'll be releasing the data on about a 3-month cadence. This will all be available on the IRIS website. You'll be able to access it the same way as you access terrestrial data. It's I should have put the station name is ELYSE, and the network is XB. XA is when it's on the deck, XB when it's on the ground. So if I got this wrong, you can ask my seismologist friends about it. I'm not a seismologist, I just play one on TV. And finally, I'd just like to thank the SEIS team. This is not, very little of this is my work except actually, getting NASA to approve this. We have a pretty extensive team of seismologists, professors, postdocs, graduate students, and this doesn't even begin to scratch the thousands of people that are behind, actually putting a spacecraft like this on the surface of Mars. And I'd like to thank each and every one of them, but I don't think I have time for that today. So thanks for your attention. So do we have time for some questions?
Yes, I think we have about 9 minutes time for questions. If there are questions from the audience, please feel free to use the mics on either side of the main corridor.
And I would like to point out that our technical session is Thursday morning, and we have several talks that will go into this stuff in a lot more detail than the brief glimpse I gave this afternoon. Just keep talking, they'll probably turn the mics on eventually.
As a seismologist, we always was told that you need to have more than one seismometer in order to locate weekends. So I guess my question is, are there any, right now there's one, but there's nothing, but are there any plan from NASA to send more, sensors like this to Mars in the near future?
There's not any plans right now. I mean, there's lots of plans in the scientific community, but NASA is sort of biding its time to see whether, how much we get from this. And it turns out that, needing 3 seismometers to do a location is one of those things that everybody knows that isn't really true. And we've demonstrated that. We've published a couple papers showing that you can do locations in at least in 2 dimensions, and if not 3, just with one station. If you have a large enough event to get surface wave trains, and particularly not just R1, but R2, and preferably R3. If you get R3, then you've got plenty of parameters. You can actually nail it down pretty well. The events we're seeing right now, we don't even have P&S wave arrivals. I mean, we're looking at, right at the limit of detection. But if we have something that on Mars only has to be maybe magnitude 4 to be globally detectable, we think that we can do a pretty good job of location.
Yeah, I too was struck by, at least at first glance, how lunar appearing the event was, which implies it's probably a fairly deep hypocenter, in which case you're not going to get surface waves. But my question was, if you low pass filter this, is there any evidence of surface waves in this signal?
I don't think so. Okay, so but first of all, it's not necessarily a deep event. The largest quakes on the moon were actually shallow events. I mean, there's lots of deep events, and they look like this as well. But you have shallow events going all the way up to, I think there's equivalent magnitude 5 or so, and it has the same character as this, and that's due not to the depth, but to the scattering in the crust, and so. Scattering makes surface waves problematic, but the question was always with the lunar stuff is whether you went to reasonably long periods, whether you would actually be able to get that stuff, because I think the Apollo seismometers basically died at about 2 seconds. I mean, so.
There were signals from the crashed spacecraft as well.
Yeah, and those are very energetically small. Yeah, and they're energetically small events. So we're certainly hoping to see surface waves. I don't think you get a really well-developed surface wave train from a magnitude 1.5 or 2, usually even on the Earth. But certainly, we'll be looking for that, and we're going to be filtering these things up, down, and sideways to see what we can pull out of it.
Thank you.
Can you explain a little bit more about your reasoning why you think these are Mars quakes? I mean, you say, okay, they look like some lunar quakes, but they don't look like earthquake, right? They look like seismic tremor, at least from the little bit of data that you've shown.
So
what is the reasoning behind it? You say this is a Mars quake.
I will defer that to my expert colleagues, but what I can say is, so the 3, what I call enigmatic events, those are relatively monochromatic. Those are very odd-looking events. The Sol 128 event that we're pegging as a Mars quake is not very monochromatic. It starts at about 2 hertz, and it has a lot of energy going up into the higher frequencies. This is very much unlike anything else that we've seen in, like I said, in 70 odd days of data. It's not correlated with any local disturbances in terms of weather, pressure, magnetic field. Certainly, there's nothing going on the lander. The lander is fast asleep during this time, and so there's nothing that we're sensing in the environment that would do it. And it has the very diagnostic characteristics of a slow rise and a slower exponential die off of the coda that we see over and over and over again in the highly scattered lunar quakes. And so this has all the earmarks of a highly scattered quake.
Okay, thank you.
Hi, good evening. It was a very nice talk, very entertaining. And I'm a postdoc working in GFZ in Germany. I have a double question. One is the Poisson process assumes that it's a low memory model, that you might have a few hundred earthquakes back to back, or you can have nothing in the next 200 years. And the second one is, how do we know that we landed in the active region, like active tectonic location? Probably, if the probe is on a very stable region, we will never see an earthquake. What information will you have a priori to decide where to land it?
Okay, so we actually did not target for an active tectonic region. The area that we land in is pretty much nondescript from a tectonic standpoint. The idea is in order to get a deep planetary structure, you actually want distant quakes. So actually you'd like to land maybe 90 degrees away from the most active region. And if you have, given that Mars is a small planet, it has half the radius of the Earth, it turns out that you don't need as much energy to be able to see something globally on Mars as you do on the Earth. And so the reasoning was that it doesn't matter where you go on the planet, you're going to get the distribution of quakes, whatever they are, coming from near and far, and give you plenty of ray paths through the interior and do the best job of constraining the interior. One of the things about this quake that we've seen has a lot of very high frequency energy, so given that it's a small event, it actually suggests that it's not very far away. And so given that we don't have any particular tectonic structures in our area, that's you have to start wondering about what mechanism caused this quake. And we don't have organized tectonic plates on Mars. There's certainly lots of faults on Mars, mostly associated with vertical deformation. But those are all questions that we actually hope to get some insight into as we go forward. One last question. Lucky you.
Hey, thanks so much. I have a question for you guys. You must be expecting like an active source, like an asteroid or something, to stimulate some energy. But did anyone think about like some kind of a source that you could trigger like monthly or daily to do a calibration or stack signal or anything like that?
Oh, of course we have. So first of all, on a local scale, we actually have that mole I was talking about that goes down 5 meters. It goes down by hammering. It's not a drill. It's a self-hammering torpedo. And so given the somewhere between 10 and 40,000 strokes, we actually hope to get a very good profile of the upper tens of meters underneath our spacecraft. In terms of other sources, we do have calculations of how many meteorite impacts that we would see over the course of the mission. Like I said, somewhere around maybe a half a dozen to a dozen if we're lucky. But that's a little bit uncertain too, because we don't know exactly what the population of impactors is at Mars's orbit, but we do expect to see some of those. There are those among us at NASA who are prodding NASA to maybe actually send basically a cannonball to Mars and impact from approach. You can get in at about, 8 kilometers per second. I recommend they aim right at the spacecraft because you never hit what you aim for, right? And it turns out about 5 kilograms of tungsten probably gives you enough energy to get a reflection off the MOHO or Mars-HO or whatever they call it on Mars. So yeah, we've been thinking about this a lot. I mean, over 30 years you get lots of wacky ideas, and that's maybe one of the less wacky ones. Okay. Well, thanks so much again.
So I'm sure Bruce and his team will be willing to entertain more questions through the meeting, but now I would encourage you all to consider attending the town hall, which is 2 levels down, and it will concern the topic of earthquake early warning in Cascadia. So hope you can make it down that way. It starts at 6 o'clock.